For most of the 20th century, astronomers believed every comet we saw belonged to our sun. Every single one. They all came from the Oort cloud, that massive sphere of icy debris surrounding our solar system, leftovers from when the planets formed billions of years ago. The Oort cloud is like our sun's attic, full of ancient frozen objects that occasionally get nudged toward the inner solar system. In old textbooks, buried somewhere in the footnotes, there was always a single speculative line. One day, we will detect an object that comes from the stars. It sounded poetic, wishful thinking, the kind of thing scientists wrote to sound visionary, not because they actually expected it to happen in their lifetimes. That changed with automation. Think about how astronomy used to work. A person would sit in a cold observatory dome, eye pressed to a telescope, manually tracking objects across the sky, taking photographic plates, comparing them by hand days or weeks later. You could only watch one small patch of sky at a time. You had to choose carefully where to look, and if something moved through your field of view while you were looking somewhere else, you'd never know it existed. Now we have surveys. Pan-STARRS in Hawaii, the Catalina Sky Survey in Arizona, and later, ATLAS, the Asteroid Terrestrial Impact Last Alert System. These are networks of robotic telescopes that scan the entire visible sky night after night, automatically comparing images to catch the faintest motion. They photograph the same regions repeatedly, and software compares each new image to the previous one, flagging anything that has moved even slightly. Pan-STARRS uses wide-field 1.8-meter telescopes, mirrors almost 6 feet across, that can capture millions of stars in a single frame. ATLAS uses smaller telescopes, but covers the whole sky twice every night. It was built specifically for planetary defense, to find asteroids that might threaten Earth. The Catalina Sky Survey has been tracking near-Earth objects for decades, methodically cataloging everything that comes close to our planet. These systems generate thousands of alerts every night. Most are false positives, cosmic rays hitting the camera sensor, satellites passing overhead, glitches in the electronics, or just stars that happen to flicker. Algorithms flag the candidates, sorting through the noise, but a human still makes the final call. Someone has to look at the data and decide whether that moving dot is a real object or just an artifact. They distinguish true movement from cosmic noise, satellite streaks, sensor errors, and all the other ways the universe can fool our instruments. For the first time in history, humanity stopped blinking at the night sky. We began to see everything that moves, every asteroid, every comet, every piece of space debris. And eventually, we started seeing things that didn't belong to our sun at all. Objects that came from beyond, from other stars. October 19th, 2017. Pan-STARRS detected an object that didn't make sense. At first, it looked like an asteroid, but when astronomers calculated its trajectory, they realized something was wrong. The orbit wasn't elliptical, it was hyperbolic. That means it wasn't circling the sun like everything else in our solar system. It was passing through, moving too fast to be captured by the sun's gravity. It came from somewhere else, and it was leaving, never to return. They named it ʻOumuamua, a Hawaiian word meaning scout or messenger from afar. The name was fitting. This was the first confirmed interstellar object ever detected passing through our solar system. But ʻOumuamua was strange in ways that made astronomers deeply uncomfortable. It had no tail, no coma. That's the fuzzy cloud of gas and dust that forms around comets when they warm up near the sun. No sign of gas escaping from its surface. By every visible measure, it looked like an asteroid, solid rock or metal, inert and lifeless. Yet it accelerated as it left the sun, ever so slightly, but undeniably. Something was pushing it, giving it a tiny extra boost as it moved away. With comets, that's normal. Gas escaping from the warming surface acts like a rocket engine, giving the comet a gentle push. But ʻOumuamua showed no visible gas, so what was accelerating it? Some scientists suggested it could be outgassing material we simply couldn't detect. Others proposed it might be reflecting sunlight with enough force to push it along, something called radiation pressure. That only works if the object is extremely thin and light, like a sail. And then there was its shape. Astronomers measured how its brightness changed as it tumbled through space, and the light curve, the pattern of brightness over time, suggested something never seen before. Either ʻOumuamua was shaped like a long spindle, maybe 10 times longer than it was wide, or it was a thin disk, flat like a pancake, tumbling chaotically end over end. No asteroid or comet we'd ever seen had that shape. Most are roughly spherical or potato-shaped. This was different, elongated, unusual, and by the time we realized how strange it was already too far away to study in detail. ʻOumuamua gave us the question, what else is out there? 2 years later, on August 30th, 2019, came the second visitor. This one was discovered not by a massive government-funded telescope array, but by a single man in Crimea named Comet Borisov. He's an amateur astronomer who built his own telescope, a 65-centimeter reflector, and had been scanning the sky for years, searching for comets. On that night, he found something moving that didn't match any known object. When professional observatories confirmed his discovery, they calculated its orbit and realized immediately what it was: another interstellar visitor. They named it 2I Borisov in his honor, proof that the universe doesn't care who's watching. You don't need a billion-dollar space telescope or a PhD to find something from beyond the stars. You need patience, dedication, and a clear night sky. And this time, the object looked like a comet should. It had a tail, a glowing coma, and all the visual signatures of sublimating ice. Ice turning directly into gas as it warmed near the sun. Finally, something that made sense. But when astronomers analyzed its spectrum, the specific wavelengths of light it reflected and emitted, they found something unexpected. Its color was wrong. Most comets from our solar system glow green because of the specific molecules in their coma. Borisov glowed blue. The spectra revealed enormous amounts of carbon monoxide, CO, and very little water. In fact, Borisov had more carbon monoxide than any comet we'd ever studied from our own solar system. Carbon monoxide only stays frozen at extremely low temperatures, far colder than water ice. That means Borisov was born in deep frozen darkness far from any star. It formed in conditions so cold that even carbon monoxide couldn't evaporate. Think about that. This object condensed out of the gas and dust around another star, somewhere in the galaxy, billions of years ago. It was ejected from its home system, probably by gravitational interactions with forming planets, and spent millions or billions of years drifting through the cold void between stars. And then, purely by chance, it passed close enough to our sun that we could see it. Now we have a third traveler, C2024 G3, officially designated 3I ATLAS, the third confirmed interstellar object. It was detected in April 2024 by the robotic telescopes of the ATLAS network, the same system built to find asteroids that might threaten Earth. At first, it looked like just another comet, but when astronomers calculated its orbit, they saw immediately that something was different. The orbit was wildly hyperbolic. Eccentricity 6.1. To understand what that means, you need to know that orbits are measured on a scale where 0 is a perfect circle, and 1 is a parabola, the borderline between being bound to the sun and escaping into space. Anything above 1 means the object is moving too fast to stay. ʻOumuamua had an eccentricity around 1.2, Borisov was about 3.4, ATLAS came in at 6.1. That's not just passing through, that's cutting straight through the solar system at tremendous speed, barely noticing the sun's gravity, on a trajectory so steep and fast that nothing could deflect it. ATLAS moved faster than Borisov and approached the sun from a completely different angle. And when astronomers pointed their spectrographs at it, they found chemistry stranger still, almost no water vapor. That's unusual for a comet. Water ice is the most common volatile material in comets from our solar system. It's what makes them bright and active when they warm up. But ATLAS showed strong spectral lines of carbon dioxide, CO2, and carbon monoxide, CO. In fact, it had 16 times more carbon monoxide than water ice. 16 times. That ratio is unheard of in comets from our solar system. It means ATLAS was born in conditions even colder and more extreme than Borisov. It formed in the outermost shadows of another solar system, far beyond where planets typically form, in a region so cold and dark that water never condensed in large quantities. Instead, carbon monoxide and carbon dioxide dominated. 3 interstellar visitors in less than a decade. After 4.5 billion years of seeing nothing but our own solar system's objects. Either we just got incredibly lucky, or these things are far more common than anyone thought. Before we go further, let's be clear about what we're actually talking about. Comets and asteroids are not the same thing. Even though they're often lumped together, asteroids are solid, dense metal and stone, impact-hungry and predictable. They're mostly found in the asteroid belt between Mars and Jupiter, though some have orbits that bring them close to Earth. They're the leftover building blocks of planets, chunks of rock and metal that never got incorporated into a larger world. When you look at an asteroid through a telescope, you see a dark, rocky surface. No tail, no glow, just a slowly tumbling piece of ancient stone. Comets are different. They're porous, filled with ice and dust, lighter than water. Their surfaces are constantly changing as they warm. When a comet gets close to the Sun, the ice on its surface starts to sublimate, turning directly from solid to gas without melting first. That escaping gas carries dust with it, forming the coma and the tail that makes comets so spectacular. A comet's nucleus, the solid core at the center, is often described as a dirty snowball, though that's a bit misleading. It's more like a fragile pile of frozen gravel held together by ice. Some comets are so porous and fragile that they can break apart just from the stress of warming up near the Sun. Asteroids orbit near the ecliptic, the flat plane where Earth and the other planets circle the Sun. Their orbits are relatively predictable. You can track them, calculate their paths decades or centuries in advance, and know exactly where they'll be. Comets arrive from anywhere. Some come from the Kuiper Belt, a region beyond Neptune where short-period comets live. Others come from the Oort cloud, that vast spherical shell of icy debris surrounding the entire solar system, stretching halfway to the nearest star. And now we know that some come from interstellar space, from other solar systems entirely. Comets often reveal themselves only weeks before they pass. A dim object suddenly brightens as it approaches the Sun, growing a tail seemingly overnight. That unpredictability makes them harder to track, harder to predict, and in some ways, more dangerous. That unpredictability makes them the more dangerous kind of beauty. Every comet and asteroid has a name, but it's not just a name. It's a code that tells you everything about when and how it was discovered. Each comet follows a strict system. The prefix tells you what kind of orbit it has. C means long-period comet, something that takes more than 200 years to orbit the Sun, often coming from the Oort cloud. P means short-period comet, something that orbits the Sun in less than 200 years and returns predictably. I means interstellar. That prefix didn't exist until 2017, until ʻOumuamua forced astronomers to create a new category. Then comes the year, followed by a half-month letter that indicates when in the year it was discovered, and a discovery number showing which object it was in that period. So C2010X1 means a long-period comet discovered in the second half of December 2010, and it was the first comet found in that half-month. After the formal designation comes the discoverer's name or mission tag. That's the human element, the credit that goes to whoever first proves its cometary nature, the one who finds the tail, who confirms it's actively outgassing, and not just a distant asteroid. If a supposed asteroid later shows cometary activity, if it starts forming a tail or showing signs of sublimation, the credit can shift. It goes to the observatory or survey that revealed its true nature. Discovery isn't just about finding the object, it's about understanding what it is. Asteroids, by contrast, are too numerous to name individually in the traditional way. There are millions of them. What matters there is precision, not poetry. They get catalogue numbers, and only the most significant or historically important ones receive actual names. But for comets, especially interstellar visitors, names matter. They mark moments in history: ʻOumuamua, Borisov, ATLAS. Each one represents the first time humanity saw something from beyond our solar neighborhood. Let's talk about the technology that made all of this possible. These discoveries didn't happen by accident. They happened because we built systems specifically designed to never stop looking. PANSTARS stands for Panoramic Survey Telescope and Rapid Response System. It's located on Haleakala in Hawaii, using two 1.8-meter telescopes, mirrors almost 6 feet across, equipped with some of the largest digital cameras ever built for astronomy. Each image captures over 1 billion pixels, covering an area of sky about 30 times the size of the full moon in a single shot. PANSTARS photographs the entire visible sky multiple times each month, comparing each new image to previous ones, flagging anything that has moved, changed brightness, or appeared where nothing was before. ATLAS, the Asteroid Terrestrial Impact Last Alert System, is smaller but faster. It uses 4 50-centimeter telescopes spread across Hawaii and South Africa, scanning the whole sky twice every night. The goal is planetary defense. Find asteroids that might hit Earth and find them early enough to do something about it. ATLAS can detect a 30-meter asteroid about 3 weeks before impact. That's not much warning, but it's better than nothing. And in the process of watching for dangerous asteroids, ATLAS finds everything else too: comets, supernovae, variable stars, and apparently, interstellar visitors. The Catalina Sky Survey operates from the mountains north of Tucson, Arizona. It's been running since 1998, using a 1.5-meter telescope to track near-Earth objects. Over the decades, Catalina has found thousands of asteroids and dozens of comets, methodically cataloging everything that comes close to Earth. MASTER, the Mobile Astronomical System of Telescope Robots, is a Russian network of small, fast telescopes stationed across multiple continents. The idea is continuous coverage. When the sun rises in one location, another MASTER telescope somewhere else is already watching. Between them, they maintain near-constant surveillance of the sky, ready to respond to alerts from other surveys or to find transient events on their own. And then there's the future. The Vera Rubin Observatory, formerly known as LSST, the Large Synoptic Survey Telescope, is an 8.4-meter eye currently being commissioned in Chile. Once operational, it will image the entire visible sky every 3 nights, going deeper than any previous survey, detecting objects as faint as magnitude 24.5. That's about 100 million times fainter than what the human eye can see. The future of discovery isn't in building larger mirrors, it's in vigilance, it's in never looking away. But there are limits to what we can see, and those limits matter. Anything approaching from the sun's direction is invisible to ground-based telescopes. The sun is too bright. Its glare overwhelms everything nearby. If an asteroid or comet approaches from that angle, we won't see it until it's already past us, if we see it at all. That's how many objects arrive unannounced. That's how the Chelyabinsk meteor in 2013 caught everyone by surprise. It came from the direction of the sun, and no one saw it coming until it exploded over Russia in a fireball visible for hundreds of kilometers. Space-based telescopes with coronagraphs can help. SOHO, the Solar and Heliospheric Observatory, sits at a gravitational balance point between Earth and the Sun, using a coronagraph to block the Sun's light and observe the region around it. SOHO has discovered over 4,000 comets, most of them sun grazers that pass extremely close to the Sun and would be impossible to see from Earth. SWAN, the solar wind. Anisotropi's instrument aboard SOHO can detect comets by observing the hydrogen they release as their water ice sublimates. It's found hundreds of comets that way, seeing them not by their reflected light, but by the faint glow of hydrogen, gas in their comas. Future observatories placed at Lagrange points, those gravitational balance points in space, could monitor the Sun-Earth line from the side, watching for objects approaching from angles we can't currently see. But even with all this technology, we're still vulnerable. Radar won't save us. Radar is precise but narrow. You can aim it only where you already know to look. It's perfect for refining the orbit of a known object, but useless for finding something new. The only real solution is more telescopes, more coverage, more redundancy. Watch the sky from as many angles as possible, as continuously as possible, and hope nothing slips through the gaps. In 2013, a 20-meter asteroid entered Earth's atmosphere over Chelyabinsk, Russia, and exploded with the force of about 30 Hiroshima bombs. The shockwave shattered windows across the entire city, injuring over 1,500 people. It was the largest airburst since the Tunguska event in 1908. No one saw it coming. The asteroid approached from the direction of the sun, invisible to our telescopes until it was already here. We got lucky. It exploded high in the atmosphere, and the damage was limited to broken glass and minor injuries. If it had been slightly larger, or if it had hit the ground intact, the consequences would have been catastrophic. That event was a wake-up call. It showed that small doesn't mean harmless. A 20-meter rock, barely the size of a house, can devastate an entire region if it hits in the wrong place. Since the late 1990s, only the United States has maintained a continuous, federally backed near-Earth object program. NASA's Planetary Defense Coordination Office tracks asteroids that might threaten Earth, cataloging their orbits, calculating impact probabilities, and researching ways to deflect them if necessary. Other countries observe in fragments: universities, private observatories, individual researchers. But there's no coordinated international effort with guaranteed funding. History has shown how close calls can slip through. In 1983, Comet ATLAS passed just 5 million kilometers from Earth, about 13 times the distance to the Moon. That sounds far, but in cosmic terms, it's nothing, and it was discovered only days before its closest approach. If it had been an asteroid instead of a comet, if it had been on a slightly different trajectory, we wouldn't have had time to react. We got lucky. Again, Apophis is an asteroid that keeps astronomers awake at night, not because it's definitely going to hit us, but because the margin of error is uncomfortably small. It was discovered on June 19, 2004, by astronomers at Kitt Peak National Observatory in Arizona. At first, it looked like just another near-Earth asteroid. Interesting, but not threatening. Then they calculated its orbit more precisely, and alarm bells started ringing. Initial calculations gave Apophis a few % chance of hitting Earth. That might not sound like much, but in astronomical terms it's enormous. Most asteroids have impact probabilities measured in fractions of a %, or more often, fractions of a fraction. A few % chance meant Apophis briefly held the highest rating ever given on the Torino Impact Hazard Scale, a level 4, indicating a close encounter deserving serious attention. Further observations refined the orbit and lowered the risk. Current models show no significant probability of impact in the foreseeable future, but there's still a scenario that makes people nervous. On April 13, 2029, Apophis will pass just 31,000 kilometers from Earth. That's inside the orbit of geostationary satellites, the ones that provide GPS, communications, and weather data. It will be close enough that its trajectory will be visibly bent by Earth's gravity, and it will be bright enough to see with the naked eye, a slow-moving star drifting across the sky. The concern is something called a gravitational keyhole. That's a small region in space that, if Apophis passes through it during the 2029 flyby, Earth's gravity will alter its orbit just enough to put it on a collision course for a future pass. The 2036 scenario, once considered a legitimate threat, depends on Apophis crossing through one of these keyholes in 2029. Current data says it won't. The trajectory is now known well enough that astronomers are confident the keyhole scenario won't happen. But the final answer will come after the 2029 flyby, when we can observe exactly how Earth's gravity affects Apophis and refine our predictions for every future encounter. Multiple missions have been proposed to track Apophis closely, either by sending a spacecraft to fly alongside it, or by landing a radio beacon on its surface. The goal isn't to deflect it, we don't need to, not yet, but to measure its spin, its composition, and its exact trajectory with far more precision than we can achieve from Earth. Because in planetary defense, precision matters. The difference between an impact and a miss can be measured in meters. And when you're calculating an orbit decades in advance, tiny uncertainties compound into huge unknowns. Precision, not panic, decides our future. Here's something most people don't realize. You can still discover a comet, or an asteroid, or maybe, if you're extraordinarily lucky, an interstellar visitor. You don't need a PhD or access to professional facilities. You need dedication, the right equipment, and a lot of patience. There are two ways to do it. The first is to build your own telescope. Not a small department store scope, but something serious, a 30 to 40 centimeter mirror, about 12 to 16 inches across, mounted on a stable equatorial mount. You'll need a good CCD camera, the kind designed for astrophotography, sensitive enough to capture faint objects. And you'll need software to compare images taken on different nights, looking for anything that has moved. Then comes the hard part. Discipline. You have to observe the same regions of sky repeatedly, night after night, comparing each new image to the previous one. Most nights yield nothing. You'll see the same stars, the same galaxies, the same background noise. But one night, if you're persistent, you might notice a faint smudge that wasn't there before, or a star that has shifted position ever so slightly. When you think you found something, you send your data to the Minor Planets Center, the international organization that tracks all known asteroids and comets. They'll verify your observation, cross-check it against known objects, and if it's real and new, you'll get official credit for the discovery. Comet Borisov did exactly this. He built his own telescope and spent years scanning the sky. And on one August night in 2019, he found something that turned out to be from another star. The second way is easier, but requires a different kind of patience. You mine the open archives of space-based observatories like SOHO and SWAN, searching their publicly available images for hidden motion. SOHO releases its data almost in real time, and anyone can access it. Amateur astronomers have found thousands of comets this way, spotting faint streaks in SOHO's coronagraph images that automated systems missed. You'll need an observatory code, a unique identifier assigned by the Minor Planets Center. You'll need to learn how to format your reports according to strict international standards. And you'll need speed. When you find something, you need to report it immediately before someone else does. Discovery credit goes to whoever reports first. Most nights, most images, most searches yield nothing. The sky is vast and truly new objects are rare. But for a few hours, maybe once in your life, you might be the only human alive who knows that something new exists, that something from beyond has arrived, and you were the one who found it. There's a fundamental limit to what we can learn from light alone. When we point a telescope at a comet or asteroid, we're analyzing photons, particles of light that reflected off its surface or were emitted by gases escaping from it. We can measure wavelengths, identify molecules, estimate composition, but we're always working with indirect evidence. Asteroids are time capsules. They're untouched fragments from before the planets formed, preserving the original material of the solar nebula, the disk of gas and dust that collapsed to create the sun and everything around it 4.6 billion years ago. If you want to know what conditions were like back then, you need to study asteroids. Sample return missions prove that each body is chemically unique. Every rock tells a different origin story. In 2010, Japan's Hayabusa spacecraft returned samples from asteroid Itokawa. The grains were tiny, barely visible, but they revealed something unexpected. Itokawa was once part of a larger parent body that had been heated enough to partially melt, separating into layers of different materials. Then that parent body was shattered by a collision, and Itokawa is one of the fragments. You can't learn that from spectra alone. In 2020, Hayabusa 2 returned samples from asteroid Ryugu, and the results were even more surprising. Ryugu is rich in water and organic molecules, the building blocks of life. It's a primitive object that never underwent heating or alteration, and its composition suggests it formed far from the Sun, in the cold outer regions of the solar system, before migrating inward. In 2023, NASA's OSIRIS-REx brought back samples from asteroid Bennu, and again, the details were unexpected. Bennu is a rubble pile, a loose collection of fragments held together by weak gravity, and its surface is far more rugged and active than anyone predicted. Each mission, each sample, reveals something that contradicts or refines our understanding. Looking from a distance only gets you so far. We can't touch interstellar visitors yet. They move too fast, arrive with too little warning, and leave before we can mount a mission. So for now, light is our only evidence. Spectra, timing, and reflection curves are the fingerprints of other worlds. We analyze the wavelengths, compare them to laboratory measurements, and infer what molecules are present. We watch how brightness changes as the object tumbles and try to reconstruct its shape. It's forensic astronomy. We're studying crime scenes from billions of years ago, with only the faintest clues left behind. But one day, maybe soon, we'll have the technology to intercept an interstellar object, to send a fast probe that can match its velocity, approach it, and collect samples before it leaves our solar system forever. When that happens, when we finally hold a piece of another star's planetary system in our hands, we'll learn things that no spectrum could ever tell us. Let's go back to Atlas, because there are things about this object that don't fit comfortably into any explanation we have. Why so fast? Its velocity relative to the Sun is extreme, higher than either ʻOumuamua or Borisov. That suggests it was either ejected from its home system with tremendous force, or has been accelerated by gravitational encounters with other stars during its journey through the galaxy. Why so steep an orbit? Most objects in our solar system orbit roughly in the same plane, the ecliptic, because they all formed from the same rotating disk of material. But interstellar visitors come from random directions. Atlas's trajectory cut through the solar system at an extreme angle, almost perpendicular to the ecliptic. That's not unusual for an interstellar object, but it does mean it spent very little time in the region where we could observe it clearly. Why the chemistry? Carbon monoxide and carbon dioxide, 16 times more abundant than water ice, is not just unusual. It's almost unheard of. In our solar system, water ice is by far the most common volatile. It dominates comet composition. But Atlas is the opposite. It's a carbon monoxide comet with traces of water, not a water comet with traces of carbon monoxide. That tells us Atlas formed in an environment radically different from our own. Maybe around a different type of star, one cooler or more distant. Maybe in the outermost reaches of its home system, where temperatures were so low that water never condensed efficiently. Or maybe in interstellar space itself, condensing from molecular clouds floating between stars. And then there's the timing. Why now? Why 3 interstellar visitors in less than a decade after seeing none for all of human history? Are we simply seeing better? That's the most likely answer. Before 2017, we didn't have automated sky surveys running continuously. We didn't have the computational power to process millions of images and flag every moving object. If ʻOumuamua had passed through in 1990 or 1970 or 1950, we almost certainly would have missed it. Now we're watching, and we're seeing what was always there. Or has the galaxy begun to send more debris our way? That's less likely, but not impossible. The solar system is currently passing through a region of the galaxy with a slightly higher density of interstellar material. Could that mean more interstellar? Objects are funneling through our neighborhood, possibly, but the statistics are still too limited to say. The data may answer these questions, if we're watching closely enough. Every new discovery refines the picture. We're building a catalogue of interstellar objects, learning what they're made of, how they move, where they might come from. 3 objects isn't enough for strong conclusions, but it's a start. And with telescopes like Vera Rubin about to come online, we'll be detecting interstellar visitors far more frequently. Maybe dozens per year, maybe hundreds. The more we find, the better we'll understand what's typical and what's truly anomalous. We didn't just get lucky. This isn't a coincidence. We built a system that never looks away. For thousands of years, humans watched the sky and saw only what was bright enough, close enough, and slow enough to notice. We tracked planets, charted constellations, and recorded the occasional comet that happened to pass nearby. But we were blind to most of the universe. We blinked, and things slipped past us unseen. Then we built machines, patient, tireless machines that photographed the same patches of sky over and over, comparing every image, flagging every change. We networked them across the globe, achieving continuous coverage. We taught computers to sort through the noise and highlight anything unusual. And we made all of it automatic, so it never stops, never rests, never misses a night because of weather or budget cuts or human fatigue. The result is that we now see everything, every asteroid that wanders too close, every comet that flares to life as it approaches the sun, and every visitor from beyond that happens to pass through our cosmic neighborhood. ʻOumuamua asked the question, are we alone in seeing objects from other stars? Borisov answered it, no, these things exist, and we can study them if we're paying attention. Atlas opened a new chapter, a story about flow, origin, and evolution, about how material moves through the galaxy, carrying with it the chemical signatures of distant stellar environments, about how different the universe is beyond our small corner of space. And maybe it shows something else too, that we're no longer passive observers of the cosmos. We're no longer waiting for the universe to reveal itself on its own terms, hoping we happen to be looking in the right direction at the right time. Now, we're watching. Actively, systematically, continuously. We've built eyes that never close, and maybe, in some small way, that means the universe is starting to observe us too. Not literally, not in any mystical sense, but in the sense that our presence is making a difference. We're finding things that would otherwise pass unseen. We're cataloging, analyzing, understanding. We're turning random cosmic events into data, into knowledge, into questions we can actually try to answer. Every object we detect, every spectrum we capture, every trajectory we calculate adds one more piece to the puzzle. We're learning what the galaxy looks like from the inside. What kinds of objects drift through the darkness between stars? What chemistry exists in other solar systems? What forces shape the evolution of matter across billions of years? This is just the beginning, the first chapter of a much longer story, and we're finally paying attention.